Welcome to week 12. This week we're going to be talking about differential equations again. The differential equations we're doing this week are really going to take advantage of your knowledge of complex numbers. We're going to start by talking about what's called second order linear equations with constant coefficients and zero right-hand side. That's a mouthful, so I'm going to write that down. I'm going to write out a general example of this type of equation, and then we'll talk about what that actually means. This is a second order equation because the highest order derivative in this equation is the second order derivative because we have d squared y dx squared. This has constant coefficients because it has these constants a, b, c multiplied by our derivatives and by y. It has zero right hand side, which you can see right here. There's a zero on the right hand side. So everything involving y is on the left side. Everything that doesn't involve y goes on the right side, and there's nothing that doesn't involve y. When it has a zero right-hand side, that's sometimes also called a homogeneous equation. Now, when you're doing differential equations like this, writing out derivatives this way gets pretty cumbersome. So there's a way we can avoid doing that all the time. So the shorthand we're going to use is with primes. So if you write 1 prime, that's the first order derivative. If you write 2 primes, that's the second order derivative. The thing you need to know is what your independent variable is, though, because this doesn't show that to you. So when you're doing real physics problems, you're going to know, and very often it's time is what your derivative is in terms of. So you might ask why we're doing second order equations before we're doing first order equations. That sounds like it would be more difficult. But actually, this particular type of equation is one of the easier types of differential equations to solve. Also, it comes up in physics all the time, so it's really important to know. So let's talk about some situations in which this form of equation does come up. Well, as you may have picked up on, I'm really obsessed with masses on springs. And that's not because I play with springs all day, that's because springs are a good model of all sorts of physical systems. Anything you can think of that vibrates, you can pretty much model as a spring. So say we have this mass on a spring, and we want to model its motion. So typically, we talk about springs and we use Hooke's law. We know that there's a restoring force for a spring. But I also want to do the case where there's a drag force. And typically, one form of drag force is that drag is proportional to the velocity. So it has this minus sign because the force is in the opposite direction of velocity. And you see it's just proportional to velocity. Some drag forces are proportional to velocity squared. It depends on the substance. We're just going to do the basic case. It's a pretty good model for a lot of physical systems if you just use this form for drag. Okay, so we want to model the motion of this mass. So we're going to use F equals ma. So we're going to sum up our forces and set that equal to ma. Well, one thing we know is that v is the first derivative of position with respect to time, and we know that acceleration is the second derivative of position with respect to time. So we can rewrite this equation. Here I'm going to use that prime notation where I'm substituting for acceleration. I'm writing x double prime because that means the second derivative. All right, we leave this x alone. And this velocity I'm going to replace with x prime because that's the first derivative of x with respect to time. Now I'm going to rearrange this so that it looks like our standard form of equation. So I'm going to move everything that involves x to the left side of the equation. Alright, so now we have a second order differential equation with constant coefficients, just like we talked about on the last slide. This type of equation also comes up for some types of circuits, but we'll get to that at a later time. So let's take a step back and look at how we can actually solve these equations. As usual, I'll start with an example. And we're not going to worry about the physical situation just for now so that you can get the mechanics of solving down. We'll come back to physical situations at another time. Okay, so the way I'm going to do this, I'm going to do it the long way to let you see where everything comes from. After you feel comfortable with that, there's a shortcut way you can do that, but I want to make sure you understand where that shortcut comes from. Okay, so to understand where everything comes from, I'm going to go back to writing this equation the long way. And I'm just going to make our independent variable x for this case. Now I'm going to factor out the y. It's kind of funny to think about doing this with derivative operators, but you can. So I looked at this and I said every term has a y in it, so I'm going to pull out that y. Okay. Now, this is something we can factor. Do you see how I'm doing this? I'm factoring this out. And for this case, I get minus 3 and minus 2, right? Because d dx times d dx gives you d squared dx squared. We get minus 2 d dx minus 3 d dx gives you minus 5 d dx. And minus 3 times minus 2 gives you plus 6. It may look a little bit funny to do this with operators, but we can do this. Okay, so normally when you factor something, you say, all right, for this to equal 0, what has to be true? This has to equal 0, this has to equal 0, or this has to equal 0. So the way this actually works out is we get two different equations. So we know that if this was true, then our above equation would be true. Or if this was true, this would be 0, then this would be 0. So let's multiply back through by y, so we have an equation that looks a little bit more in a familiar form that we know how to solve. These are both separable equations. Okay, so this is your warm-up. I want you to solve each of these separable equations for their general solution. It's been a while since we've done that, but you need to get up to speed on that. Let me write that on the next page. Okay, so I want you to pause the video and solve each of these for the general solution. Okay, so when you have a separable equation, you want to put all the y parts on one side and all the x parts on the other. Then you integrate both sides. And you only have to put your arbitrary constant on one side. We want to actually solve for y. Now remember, this is the solution, true, but I don't like it in that form. It's not easy to work with. So I change this to this form. Alright, hopefully you see that number 2 is of the exact same form as number 1, except it has a minus 2 instead of a minus 3. So I know that the solution to this one, because I know it will work out the exact same way. Okay, so we know then that each of these solutions we just found are solutions to the equation we have originally. So I'm going to call this one y1 and this one y2. So our general solution to the original equation is a linear superposition, which is a fancy way of saying adding up, of the two solutions we just found. I'm going to change my c's because these arbitrary constants are not the same. So I'm going to change this c to a. I'm going to change this c to b. So we have a e to the 3x plus b e to the 2x. Now, in order to find out what a and b are, we would need some initial conditions or boundary conditions, and hopefully you still remember how to do that. Next thing we're going to do is I'm going to show you how to solve this using the shortcut. So this is your general solution. This is what we are looking for. But hopefully you can kind of see just by looking at number 1 and number 2 right here that the same thing's going to happen every time you solve an equation of this form. So you don't have to go through all of these steps every single time. Alright, I'm going to show you the general version of the shortcut, and then we're going to apply it to the problem we just did. Okay, so this is our general equation. This is our differential equation for any old arbitrary constant. Now I'm going to write what's called the characteristic equation. So where y double prime is, I write r squared. Where y prime is, I write r. Where y is, I just take that away. And what we do is we find the roots r1 and r2 for this solution. And the general solution is going to be, okay, so I want you to take a minute and think about where this comes from. So remember what we did is we factored the y out of everything, and then we found two factors, and you could alternatively use the quadratic equation to find the roots. It was just a little different from what you're used to looking at, because instead of having something simple like r, we're looking at d dx. So think of r as d dx. And then we're always going to end up solving a differential equation that's separable and gives an answer of the form a e to the rx. What changes between different versions of this equation is what those roots are. I hope that makes sense. Spend a little bit of time thinking about it. Okay, let's apply this method to our example. And hopefully this will make it a little bit more concrete for you. Okay, so you see we got the same answer we got going the long way. We're just avoiding solving that same separable equation over and over again, because it's always going to give us a solution of the same form. Okay, now I'm going to give you two examples to try yourself. You're welcome to do these the long way the first couple times you do them, if that makes you feel more comfortable. But I expect you to get to the point where you do this the shortcut way, because I don't want these problems to take you a really long time to do. So take a few minutes and try these out, and then press play when you're ready. So the first thing I'm going to do is write the characteristic equation. Then I'm going to factor. And remember, if factoring doesn't work out, you can always use a quadratic equation to find your roots. Okay, so that's our general solution. Let's do our next one. There's our characteristic equation. We factor this one, which is a little bit harder to see how to do, but not too bad. So then our general solution. So let's take a minute and think about what these solutions mean. So this has a little bit of exponential decay and a little bit of exponential growth. But the exponential decay is overall stronger than the exponential growth, which is generally the same situation you're getting here. And if you want to think about that more, I do encourage you to graph these solutions. Okay, so this is what happens when you get two different real roots. It's common enough. I don't think it's the most interesting case, but we need to look at a couple other special cases. So sometimes what will happen is that both of your roots will come out to the same number. Another way of saying this is that there's only one root. Let's look at an example where that could happen. That's a double prime. Somehow it came out looking like a pi. Okay, we write our characteristic equation. Well, this factors out to r minus 3 times r minus 3. The only root we get is r equals 3. In this case, the solution is of this form. For the most part, this still just looks like exponential growth, but we have a is multiplied times a linear term, and b is only multiplied by the exponential term. If you want to know why this is true, let me know, and I'll do a derivation next week. Now, I'll just give you one like this to try for yourself. It's not too hard. Unless it's really bothering you that you don't know where that came from. In which case, just let me know. Alright, so just pause the video and find the general solution to this differential equation. So as always, we write our characteristic equation. When we factor this one, we just get r plus 2 squared. So r equals minus 2 is our only root, which means our solution is of the form ax plus b e to the minus 2x. Okay, and of course what you get when you graph these depends on what a and b are going to be, but you can still try it out for a couple of different values and see what happens. Alright, now we're going to get to what I think is really interesting, which is when your roots come out to be imaginary or complex numbers. And this is why it's really important that we've covered complex numbers already. Alright, let's write out our example. It is really not obvious how to factor this one, so I'm going to use a quadratic equation, which I always remember by singing a little song in my head that goes to the tune of Pop Goes the Weasel. I'm sure you all have your own tricks. I had one student that drove him crazy whenever I sing a song for this, so I will spare you. Okay, so if you work this out, what do you get? You get, well, this is 16 minus 36, it gives you minus 25. So what you end up with, and if you want to work out the algebra for yourself, just pause the video and take a minute and verify that you get the same thing that I got. Okay, so these are our roots, 2 plus or minus I to the square root of 5. And we can do the same thing we always do to write the general equation. So this is technically the solution. And we could leave our answer this way, but I don't want to because it's really not obvious what this means for a physical situation. So I'm going to rewrite this so we can actually see what this solution means. So first thing I'm doing is separating the real and imaginary parts into two separate exponentials. Now I'm going to factor out the real exponential. Okay, so we have exponential growth out here, and then we have complex exponentials on the inside, which, if you remember, we talked about before, means that there's oscillations going on. So let's go ahead and write this in terms of sines and cosines. So I want you to do this part yourself. And let me give you a little bit more detailed instructions, and I'll do that on the next page. Alright, so we have an equation of this form. I want you to rewrite this in terms of sines and cosines. And the way I want you to do that is by using Euler's formula. So where we have e to the I square root of 5x, okay, use this, plug in square root of 5x for your theta. Do the same thing on this term. Clean it up as much as you can, but after you have a go at it, press play and I'll talk about how I like to clean it up, if you can't decide what your favorite way to clean it up is. Alright, so press pause and give it a go. Okay, let's write this out. Okay, so that's our basic plugin. Now I'm going to start cleaning it up. I'm going to leave the a terms alone for the moment. So when I look at the cosine term, I know that cosine is an even function, so cosine of minus square root of 5 times x is the same as the cosine of plus cosine of the square root of 5x. So I can just get rid of that minus sign on the inside. But I know that sine is an odd function, so I know that sine of minus square root of 5x equals minus the sine of square root of 5x. So I'm going to pull this minus sign out. Okay, now we can do a little bit of consolidating. Now we have two terms with cosine square root of 5x. So we have a plus b. And we have two terms with the sine. Now remember, a and b are arbitrary constants. I, though it is the imaginary number, is still a constant. So I'm going to define new constants. I'm going to define a constant c that is the same as a plus b. I'm going to define a constant d that equals I times a minus b. This doesn't really tell you whether c and d are real or imaginary numbers. If a minus b is a complex number, or a minus b is an imaginary number, then d is a real number. But we'll worry about that more when we come back to looking at real situations. One fun way to think about, well, I think it's fun to think about, is I is a phase shift of pi over 2. Because this is I in rectangular form, this is I in polar form. That amuses me. But we will do more with that later. So the important thing is, now that it's really clear that our solution that on the previous page just had some complex number in the exponent, we didn't know what that meant. Now we can look at this and know what this means. This is an oscillation that is exponentially growing. So we have a shell that grows exponentially. I'm not perfect at drawing this, but hopefully you get the idea. So you have an oscillation whose amplitude is growing. Let's say e to the 2x was e to the minus 2x instead, then you would have exponential decay that's oscillating, which is something you see in real life a lot actually. Forgive my imperfect drawings. So anytime you have something that vibrates that eventually damps out, we've just written a differential equation and a solution to that differential equation that models that situation. This is really important. It models all sorts of real physical situations. And now that you can do differential equations, you can see where that comes from. Okay, this is one of my favorite things. So whether you want to write your end solution in exponentials or in terms of sines and cosines really depends on what your next step in your calculation is. If this is your end result and you want to physically interpret it, I'd go for sines and cosines. But if you need to use that result in further calculations, I'd keep it in exponentials because doing math with exponentials is easier than doing it with sines and cosines. Okay, now I'm going to give you a simple case where the roots are just imaginary, just so you can see what that looks like. Okay, now solving this sort of thing isn't that hard, and we've actually looked at this equation a couple of times earlier this semester. You can check your notes to see, but we're going to solve it our new way. Alright. Now the biggest mistakes my students have made with this in the past is that they'll write r squared plus 16r instead of r squared plus 16, so just make sure you're being careful. Okay, so this means our solution. And if we write this in terms of sines and cosines, we just get, and you're certainly allowed to use a and b for your constants when you're doing sines and cosines. I'm just using c and d instead of a and b because a and c and b and d are all different numbers. So we know that when we just see complex exponentials like this, that all we're getting is oscillations. There's no exponential decay or exponential growth. This is pure oscillations. And there are some situations where damping is low enough that that's a reasonable approximation. Okay, so the last thing we're going to do today is I'm just going to give you two examples where your roots are either imaginary or complex, and you can find the general solutions. Alright, so find the general solutions to these two equations, and press play when you're ready to go again. Okay, let's write our characteristic equation. Remember, it's just 36, no r. So r equals plus or minus 6i. This is going to give us a pure oscillation. So you can write your answer either in this form or as sines and cosines. It's up to you. Also, in some situations, like if you're using boundary conditions versus if you're using initial conditions, that determines which form you want to write this equation in as well. Okay, let's do our next one. Alright, I'm going to use the quadratic equation to solve this one. So my roots are, so the most basic form for writing our solution, which is not the most informative version. Okay, you're not wrong if you leave your solution like this, but it's really not my favorite. Okay, this is a useful form. Okay, so any of these three solutions is a correct solution. But I'm not going to be excited if we leave it in the first form. Okay, well that's where we're going to stop for the day. I'm really excited we covered this because this applies to so many real physical situations. Alright, see you next week, and let me know if you have any questions in the problem solving discussion.